So back to our examples here again. If we want to calculate the displacement, we take the final position, which is 1 meter, minus the initial position, which was position -2. So we're doing minus -2, which, as you recall, is adding. So that equals 3 meters. Okay? The displacement that we had from going from here to here is 3 meters. And since it's a positive number, that means it's in the positive direction. Okay, now if we turn it around and we start here and go backwards, well, now we're going to have the final position is -2 minus the initial position, which was +1. Now we have -2 minus 1, which equals -3 meters. So the answer we get tells us that we went backwards. That's what that negative sign means. Okay, -3 meters. Likewise, if we talk about the one where we started here, went all the way out to position 3, and then came back. So it's the one where we ran out and then came back again. We saw that it's the displacement was -2. -2, that's what we got. Well, what does this look like? All we care about is the final and the initial position. That's all that shows up in the equation, so that's all we care about. So the final position is -3. The initial position is -1 minus -1 equals, so this is 3 plus 1, which means -2. -3 plus 1, -2 meters, which means that on our whole journey, we went 2 meters in the negative direction. All right. That is distance versus displacement, and you got your displacement equation, which is a keeper. By the way, this is the way I always introduce equations. I write out the equations and I define the variables, okay? And in the future, I will just call this final position, initial position. I won't actually talk about the little subscripts. Okay, we're going to need a blank sheet here pretty soon, so we'll come back to this one. Let's go back to our presentation. Okay, let's see, distance versus displacement. Yeah, so we saw that one. That's good. Let's see, displacement equation. We got that. That's the one we just did. That's super. And now we'll talk about speed. Okay, speed. And this is getting in preparation for speed versus velocity. And I guess to be consistent here, I should do the same thing that I did before. Speed and velocity, that's a scalar and a vector. And velocity is the vector quantity. That's the one where we care about the direction. And speed is the scalar quantity. And this is a really good one to remember which is which, okay? Speed starts with S, that's the scalar quantity. Velocity starts with the V, that's the vector quantity. So when we talk about velocity, we care about the direction. When we talk about speed, we don't care about the direction. So a car going around a racetrack isn't getting anywhere. It's just going around and around really fast and not going anywhere. But its speed has meaning. We can talk about an Indy car going 250 miles an hour all the way around the track. But if we talk about the velocity of that car, if we're only talking about the starting and ending point, then it's going to be 0. The winning velocity of the Indianapolis 500 every year has been 0 because the starting line is the finish line. And they start where they finish, which means they didn't get anywhere. Okay? But the speed has meaning, and the speed gets faster and faster every year. Okay, so let's see, what does this look like? Because we have speed and velocity equations as well. So let's go to here. We will expand this out again. Okay, so speed equation. Speed equation. There we go. Keeping in mind that this is the scalar quantity. That's the scalar. And here it is. The speed equation is V is equal to delta x over delta t. All right, what does this mean? Okay, delta x, that's a change in position. That's a unit of distance. And delta t, that's a time. It's a unit of time. So any speed that we describe is always some unit of distance divided by some unit of time. How fast was your car going when you drove to school this morning? Well, probably 30 miles per hour. Miles per hour. It is a distance divided by a time. How fast do your fingernails grow? probably what, like 2 inches per year, right? 2 inches per year. It's a unit of distance divided by a unit of time. All speeds fall into those units. Now, our standard SI units are normally meters for distance and seconds for the time. And that means that the units for speed is always going to be meters per second. Okay? And X is meters and time is seconds. Okay, so if you want to break it out into terms, we have a meters times 1/seconds, which makes meters per second. So your units are going to be meters per second. Okay, so let's go back to our scale here. So 0, 1, 2, 3, 4, -1, -2, -3, -4. And we start here and we end here. And let's say we do the trip in 4 seconds. Okay, so our time is going to be 4 seconds. We'll just use that just for just so we always have a good number to go with. Okay, so speed is a distance divided by a time. The distance is 1, 2, 3. So that's going to equal 3 meters divided by 4 seconds. And we don't use fractions in physics. Almost never use fractions. So we want to break this down to a decimal. So that's going to be 0.75 meters per second. And you put a box around it when you get to the right number. Okay. Now, what if we started here and went back to here? Or actually, let's go from here to here. That'll work. So we start at position 3 and go to position -1. And I'm going to do this using the GFEW format so you can see how it works, how I want it to be. So this is the situation. We're told that it went from this position to this position in 4 seconds, and we want to find the speed. Okay, obviously that'd be written in a paragraph in the book, but whatever, that's what we got. So G, remember, is given, and we say it is 4 meters. We can figure that out from the diagram. 1, 2, 3, 4. 4 meters in 4 seconds, because that's given 4 seconds. That's all the information that is relevant, so that's all that we write down. We are supposed to find, that's the F, the speed in meters per second. Remember, we always write down the units that we're supposed to get so we can do our final check. Now, the E and the W, very often we kind of do them together because one blends into the next. So the equation that we're using is this one. V equals delta X over delta T. That's the equation. And then the work is where we plug our given values into that equation. So in this case, that's going to equal 4 meters in 4 seconds divided by 4 seconds. 4 divided by 4 is 1, so we get 1.0 meters per second. And we put a box around it because that's how we know we got to the end. That tells us the answer. And the last check always is to make sure that the units we got, meters per second, are the units that we were supposed to get. And in this case, that checks, so we're good to go. Where this becomes an issue is like if we say you drove from your house, 2 kilometers in 5 minutes, and we want to find the answer in meters per second. Well, then you're going to have to do some conversions. How many meters is 2 kilometers? How many seconds is 5 minutes? So there's going to be some conversion factors in there, but you want to get down to meters per second. Okay, so that is the speed equation. That is the speed equation. And delta X for the speed equation is always the distance, which, as we said before, is a scalar quantity. The direction doesn't matter when we're talking about speed. So if we turn this around and we went this direction, we started here and ended here. Well, I guess I already did that one because we went in this direction. Because we were going in the negative direction, but the answer comes out to be a positive number because distance is always positive. We don't care about the direction. Okay. Now, how about velocity? Remember, velocity, that's the vector quantity. We do care about the direction in this case, but it's the same equation. We use the same equation. That's actually why they use V for speed, because we also use V for velocity. Usually we work with velocity. And if the distance doesn't matter, we just kind of ignore the direction, Okay, so for velocity, it is displacement displacement is our delta x. Okay? And that can be positive or negative depending on whether we're traveling forward or backwards. All right? So to use this same setup that we did before, let's see, given 4 meters in 4 seconds, we're supposed to find velocity in meters per second. The equation is v equals delta x over delta t. And this time, the displacement is -4. -4, because we're moving in the backwards direction. We're moving in the backwards direction. We have to indicate that. So it's going to be -4 meters divided by 4 seconds, and we wind up with -1 meters per second. We check to make sure that our units are what they're supposed to be. So yeah, -1 meters per second. Now notice what the equation does is if you get a negative answer, that tells you that the velocity was in the negative direction. And it only works if you're using displacement, which is the vector quantity. So if you put vectors into your equation, you're very often going to get vectors out of the equation. Up here, it was only scalars. We were using a scalar for distance and a scalar for time, and so our speed was a scalar quantity. To repeat what I just said, displacement is a vector, and a vector divided by a scalar very often will turn out to be a vector. So it's kind of mathematically rigorous. Okay, let's see. Let's do this one here. Take that one down. Okay, so we got velocity versus speed. I think that takes us to the end. So let's go to here. And yeah, that's it. Okay, so representing motion. We did motion diagrams. You saw how those things work and some idea of how to use them. We talked about the difference between vectors versus scalars. We'll be seeing those again and using them a lot. Distance versus displacement. Remember, distance is the scalar quantity and displacement is the vector quantity. That's one you just have to memorize. You just have to know that. And then speed versus velocity. Also, scalar is the speed and velocity is the vector. That's easier to remember because it's a V and an S, and that makes it easier to remember. Okay, that should get you ready for the homework assignment number 2. I will check it next time I'm in, which will probably be, well, yeah, I'll check it next time I'm in, and you guys have a good day.